This is a video on tests of significance. And tests of significance are going to use this ubiquitous term, p-values. So a reader wrote in to the Ask Maryland column to say that his grandfather told him that in 3/4 of all baseball games, the winning team scores more runs in one inning than the losing team scores in the entire game. This phenomenon is called a big bang. Now, I'm a baseball fan, and I think that sounds like really high. I've watched a lot of baseball games. I don't think that's true. And Marilyn, the columnist, responded, oh, she agrees with me. She says, it also seemed too high to be believable. So we're going to say, let pi being, remember, our population proportion, be the proportion of all Major League Baseball games in which a big bang occurs. Now, I'm just going to pause for 1 second here and remind you of something. Populations, let's get it right here. Populations is generally what we want to study, but they're almost always too big to get accurate data from. So what we do is we take samples from populations, and those samples will give us statistics. Statistics, there we go. A statistic is a number. Okay, a statistic is a number. If it is a categorical type of a thing we're looking for, frequently it will be a proportion. Not always, but frequently it'll be a proportion. If it's something quantitative, the type of statistic that we look at very frequently is a mean. Okay? But those are numbers. And then from those statistics, if we've done everything right, we can then infer a parameter to a population. So we start with the population, we take a sample, we do it randomly, we do all the proper steps to make sure that there's no bias involved in our sample, and then our samples produce statistics, which are numbers, and if we've done everything right, then we can say, well, based on these statistics, the parameter for the entire population is such and such. So just a little background vocabulary there. So back to the problem. Grandpa made an assertion, and they're saying restate his assertion as the null hypothesis. Now, null hypothesis is a term that just in and of itself, language-wise, can be a little bit confusing. And a good way to think about it is the null hypothesis is what we are setting out to find out if we can nullify it. Can we gather enough evidence to show that this is nullified, that it's not true? So we say the null hypothesis, H sub 0, well, that is that pi is equal to 0.75. Grandpa is saying 3/4, 0.75 of all baseball games have a big bang. And Marilyn, the columnist, she's saying, I don't think so. I think it's too high. Her alternative hypothesis, H sub A, is that pi is less than 0.75. Now, for our purposes, the null hypothesis will always be H sub 0 and pi equals something. The alternative hypothesis will be that pi is less than something, is greater than something, or is not equal to something. So kind of remember that. Null hypothesis, we're saying pi is equal to something. and we're setting out to say, well, can we gather enough evidence to reject the null hypothesis? We are never proving the alternative hypothesis. You know, proving something with statistics is very difficult to do. You can make a very strong case, but generally speaking, proof is something that is beyond our ability for an entire population. But we can gather enough evidence to say, the null hypothesis, we are rejecting it. So what we're going to do is we're going to set out to get a sample and then a statistic. So we randomly select, we randomly select 1 week of the baseball season, and that turned out to be this particular week, just 1 week out of a whole season. And we looked at the 95 games which were played and found out which ones had a big bang and which did not have a big bang. So this 95 right here, that is our N. That is our sample size. So they kind of didn't give us a piece of important information, which is actually on the next page here. It says, of the 95 games in our sample, 47 contained a big bang. So there is our statistic, right? That is our proportion. That is our p hat, our proportion from the sample. And our p hat is equal to 47 divided by 95, which is equal to 0.495. So coming back to this here, it says sketch and label the sampling distribution for the sample proportion gains contained in a big bang. Actually, I could have done that without finding the statistic from our sample, because we're now following the process for a test of significance. So let's kind of extend this page just a little bit. We'll go up to the top again. And so we are assuming that Grandpa is correct. We're saying, Grandpa, you are correct. That is our null hypothesis. So we think that baseball games are going to be distributed, got it, with random sampling, and that right in the middle here is going to be our 0.75. So if Grandpa is correct, then the vast majority of our games, say in the big, the real fat part here of this normal curve, the vast majority of our games are going to be right around 75% of them are going to have a big bang. Or put differently, I might say that if I go out and I sample a whole bunch of different 95 game samples, so a whole bunch of different weeks where 95 games are played, that I'm going to find that the proportion of them that had a big bang, most of them are, again, right in this 0.75 neighborhood. But I need to be a little bit more precise, and one of the things I need to do really before I can even start this problem is see whether or not the central limit theorem applies. And for that, I have to look at pi times n. Make sure that that is greater than 10. And 1 minus pi times n. Make sure that that is greater than 10. So I think I can call my little calculator right here. And let's clear this stuff out. And pi is 0.75. And I'm going to multiply that times my n, which is 95. And I find out, well, that's 71.25. So that is definitely greater than 10. And I'm going to go 1, let's use a parentheses here. Parentheses, 1 minus 0.75, and I'm going to multiply that times 95, my sample size, and I find out that that is 23.75, so that is also greater than 10. So my central limit theorem is going to work here because we randomly selected the week, randomly selected our sample, which is 95 games, and our conditions for the central limit theorem have also been met. Our numerical conditions have also been met. So I'd like to fill out my normal model here. And I know I want to get, 1 standard deviation, 2 standard deviations, 3 standard deviations, positive, and then negative. So, -3, -2, -1. That's 0. That's my mean. 1, 2, and 3. And in order to calculate the standard deviation, I'm going to use the formula pi times 1 minus pi divided by n and taking the square root of that. So in this particular case, it is the square root of 0.75 times 1 minus 0.75 divided by 95 and taking the square root of that. So if I do that over here on my calculator, I go 0.75 times 0.25. I divide it by 95, and then I take the square root. And I find out that my standard deviation, I think I did something wrong here. Yes, I did. I didn't divide it by 95. That didn't look right at all. So trying again, 0.75 times 0.25. Now, divide it by 95. That works better. And now I'm going to take the square root. And there we go. That's a lot better. So 0.0444. So this is equal to 0.0444. So I'm going to kind of label my diagram. And I like to do this with the actual standard deviation numbers instead of like 5s or 10s because it makes it a lot easier to see here. So I'm going to go take my mean, which is 0.75, and I'm going to add 0.0444. And I kind of like to do it 3 times in a row so I can get 1, 2, and 3. So 0.0444, and then 0.0444. And I find out that 1, 2, and 3 standard deviations are 0.7944, 0.7944, and then 0.8388, 0.8388, and then 0.8832. And now I'm going to do it to the other side. I'm going to go 0.75 minus 0.0444 and do that 3 times. And I get on this side now, I get 0.7056. I get 0.6612. And 0.6168. So now I have a nicely labeled sampling distribution based on Grandpa's null hypothesis. So in other words, if Grandpa is correct, then this would be the distribute. Every time I went out and got a sample of 95 baseball games, for example, we know that using the empirical rule that this is 68%. 68% of the time, the proportion of baseball games that had a big bang would be between 70.56% and 79.44%. So that's using the empirical rule. And That's what this sampling distribution is kind of representing, is that for samples of 95 games, the vast majority of them are going to fall right around the 75% having a big bang or not. Well, now I'm going to look at our actual sample. We discussed this a little bit earlier. 47 contained a big bang out of the 95 games. So my p hat, my actual sample proportion, was 0.495. Well, is that, so that's p hat, and it asks, is this sample proportion less than 3/4? Well, yeah, I would say 0.495 is definitely less than 0.750. So I'm going to kind of take my picture here, put it back right there. And I'm going to put my actual proportion on this diagram. Well, and that's going to be hard to do because 0.495, well, is like way over here. 0.495 is way over here. That's like, well, way less than 3 standard deviations away from what Grandpa was saying here. So it's not looking too good for Grandpa's hypothesis, but let's continue on and see if we can do this in a proper statistical manner. So what we need to do to carry out this test of significance is we have to calculate our test statistic. That is the z-score for our p hat. And then we're going to use our calculator to find out its p-value, which represents the area under the curve of the normal model at that z-score. So our test statistic, well, see, we know that we go z equals y minus y bar over s. So our y, that is our actual statistic, is 0.495. And then I'm subtracting the mean, which Grandpa said is 0.750. And then I'm dividing that by our standard deviation of 0.0444. So I'm going to get a z-score. Well, you can see I just did it over here on the calculator. I got a z-score. My z-score is way low. It is negative 0.574. Wow. So there, if I was to even try and shade the area under the curve, I mean, this curve is already, by the time I get out here, is already pretty flat. I mean, there's a very, very little tiny area under here that represents the probability of getting this statistic of 0.495 if, in fact, the population proportion is 0.75. So the likelihood, well, let's just figure it out. I'm going to use the calculator, and I'm going to go normal CDF, which calculates the area under the curve. And my left z-score is going to be negative 99 because I want to get all of the area going that way. And my right z-score is going to be negative 0.5, no, what did I get 0.574? Negative 5.74. Let's rewrite that here. Negative 5.74. I put my decimal in the wrong spot. And so that tells me that the area under the curve, let's just do it on the calculator. Distribution, normal CDF, negative 99, comma, negative 5.74. Wow, that's a number. I have this e to the negative 9. That means I have to move this decimal point over 9 spots. That is essentially an area under the curve of 0. Wow, that's like almost nothing. So to put this into the proper terms, my test statistic was negative 5.74. That is the z-score of my actual sample on the distribution based on the null hypothesis. And my p-value represents, since I was looking for getting a score, a number that small or lower, my p-value here is essentially 0. It's this number, 4.75 times 10 to the negative 9th. So following this procedure here, based on this p-value, would you say that the sample data provides strong evidence to support Marilyn's contention that the proportion cited by the reader's grandfather is too high to be the actual value? Well, so again, it's a bunch of double negatives here, but that's just the way we have to do it. Yeah, my grandfather said, grandfather's hypothesis, h sub 0, was that pi was equal to 0.75. And based on this, the probability of us getting 47 out of 95 games having a big bang is so low based on grandpa's assumption that we are going to reject the null hypothesis. And even if we had a test of significance, which is alpha is equal to 0.01. So a very small test of significance. We're saying that in order to reject the null hypothesis, our p-value has to be below this number. Well, our p-value is below this number. So I say we have pretty firm evidence to reject grandpa's hypothesis, the null hypothesis. So Marilyn's going to come back. She says, well, grandpa is wrong, right? And she says, what I think is that the actual population proportion of Big Bang games is 1/2. So Marilyn is saying, I want to set out a new null hypothesis, and I want that as pi is equal to 0.50. And I want to test it. And I'm going to test it in a two-sided way. So not just that it's going to be greater than 0.50 or less than 0.50. I'm testing it, and I'm saying that pi is not equal to 0.50. Now, if I'm going to find a p-value that is, let's say here's 0.50, and I get a statistic, and I say it's over here. My p-value is this number that's less than 0.50. And if I was to say, so this would be a pi less than 0.50 alternative hypothesis. And if I had an alternative hypothesis that pi was greater than 0.50, well, then it would be on this side because this is greater than my null hypothesis. But when I say that it is not equal to 0.50, pi not equal to 0.50, I actually add both of these p-values together because I'm not saying that it's greater than or less than, I'm just saying it's not equal to. So so my p-value is going to be, has to be larger to prove that. And so it's a little bit harder to prove since it's a larger p-value. And the smaller the p-value, the more likely it is that you are going to reject the null hypothesis. So a small p-value, let's look at the word. P-value, I think of it as probability. Probability value. What's the probability that you could actually get such a thing? And on a sample statistic. And so if it's a really small probability, that's when I can reject the null hypothesis. If I have to go two-sided by just saying it's not equal to, well, that's even harder then to reject the null hypothesis. So let's see how Marilyn's turns out. So I'm going to draw the normal model for Marilyn's hypothesis. And so in the middle here, she has a 0.75 0.50, and I want 1, 2, 3 standard deviations on either side. So here's 0, 1, 2, 3, -1, -2, -3. And I have to recalculate the standard deviation because now I'm using Marilyn's null hypothesis instead of Grandpa's. So I'm going to have the square root. Come on, I want a different color here. I'm going to have the square root of 0.50 times 1 minus 0.50, which is again 0.50, divided by our 95 games. And that, when I work it out, equals 0.0513. So that is my standard deviation here for this model. So filling in my numbers, I get these numbers I just put in here in blue, and I'm just going to kind of mark where our 0.495 is. We can kind of see it. Well, 0.495 is going to be right around here. That's our statistic. 0.495. That's our number of games out of 95. So my statistic is on the lower side of my null hypothesis. So I am concerned about the probability. Kind of bear with me here a little bit. This is the probability of having a sample of 95 that has 0.495 proportion of Big Bang games. So let's find out what that probability is right there. So I'm going to go over here to my calculator and, oh, wait a minute. Before I can find that probability, I need to find the z-score for the 0.495. So, and I'm going to use my formula here of z equals y minus y bar over s. So my z-score is equal to 0.495 minus 0.50 divided by my s of 0.0513. And I get a z-score here of negative 0.10. So going over to the calculator, second distribution, I'm going to calculate this area under the curve right there. That's my probability of getting a sample of 95 games that has 49.5% or less Big Bang games. So that's number 2. So I'm going from negative 99 to negative 0.1. And I find that this probability right in here is 0.46, so about 46%. But remember that my alternative hypothesis was not equal to. So not equal to, I have to consider both sides. Two-sided p-value. So since it's symmetrical, I know that this z-score is going to be positive 0.10, and I know that this proportion is going to be positive 46% or 0.46. So my p-value is equal to about 0.92. Well, that's a very large p-value. That's saying there's a very large probability that if the population proportion is half the games have Big Bang, well, there's about a 92% chance that what I got less than or even greater than 0.50 could happen just by randomness. So I cannot reject the null hypothesis. I'm not proving the alternative hypothesis, but I cannot reject the null hypothesis. There is no reason to doubt that what Marilyn conjectured, that the actual population proportion is 0.5, I have no statistical evidence to doubt that that could very well be true. I'm not saying it is true, but it could very well be true.